Hello! In this video, we are going to prove the intermediate value theorem, which says the following. Let I be the closed interval a comma b, and let f be a function from I to the real numbers, and we'll assume f is continuous on I. Suppose w is a real number, such that f of a is less than w is less than f of b. Then there exists an element c in the open interval a comma b, such that f of c is equal to w. Now first, let's get an intuition for what this theorem is saying. So let's first draw our closed interval a comma b. So just like this, and then we're going to say that our function f looks something like this. So as you can imagine, this is f of a, this is f of b, and in this case, we have f of a is less than f of b, because we are given that this inequality is true, right? And this inequality implies that f of a is less than f of b. Now, we're given a real number w between f of a and f of b, and let's say that w is about right here. And what this theorem is saying is we can find an element c in the open interval a comma b, such that f of c is equal to w. So we can find an element in this interval which is not one of the endpoints, say this one, and the output value yielded by this value c, so f of c will be equal to w. And that is really what this theorem is telling us. Now, this value c is not necessarily unique. There could be many different values from c whose output values yield w. For example, if instead we take c to be this guy, well then, as you can see, f of c is also going to equal w in that case. So what this theorem is telling us is we can find at least one value for c in the open interval a comma b such that f of c is equal to w. And that is really the essence of this theorem. So now we're going to prove it. But first, what does it mean for our function to be continuous on I? Well, intuitively, what that means is we're able to draw our function from a to b without lifting up our marker or pencil, right? That's what it means intuitively. But if we want to speak of what this means more formally, well, to say that f is continuous on I means that f is continuous at every point in I. Okay, so then, given a point k in I, what does it mean for f to be continuous at k? Well, to say that f is continuous at k means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the domain of our function, if the absolute value of x minus k is less than delta, then the absolute value of f of x minus f of k is less than epsilon. Right, so this is what it means by definition for f to be continuous at k. Okay, so with this context, let's begin proving this theorem. To start out the proof, let's consider the following set. We consider the set S, which is the set of all elements x in I, such that f of x is less than w. Now, according to our diagram, the set S will be as follows. Right, so this is what S will look like for our diagram. Because, starting right here, f is less than w, then f is greater than w, then f is less than w, f is greater than w, f is less than w, f is greater than w, f is less than w, and then f is greater than w. Now, we expect S to be non-empty and bounded above. The reason why S is non-empty is because, for example, A is an element of S. To see how A is an element of S, well, first of all, we know that A is an element of I, and we know from our hypothesis f of A is less than w. So in the definition of S, if we take x to be A, well, A is an element of I, and f of A is less than w. So A satisfies all the requirements to be an element of S, and therefore A is an element of S. and that tells us S is non-empty. And next, we can show S is bounded above. In other words, we can show S has an upper bound. In fact, B should be an upper bound of S. What does it mean for B to be an upper bound of S? It means that every element of S is less than or equal to B, right? And it's pretty easy to show that. If we give ourselves an arbitrary element, X in S, well, by definition of S, we know that X must then be an element of I. And to be an element of I means you're greater than or equal to A and less than or equal to B. So in particular, X is less than or equal to B. So what this means is, given any element X in S, we have that X is less than or equal to B. And that shows B is an upper bound of S. So now, we see that S is non-empty and bounded above. Well, if we recall, every non-empty subset of real numbers that is bounded above has a least upper bound. Right? That's called the completeness property of the real numbers. So S must have a least upper bound. And so we're going to call the least upper bound of S by the letter C. Another name for the least upper bound is the supremum. And so we're going to let C be the supremum of S. Now, in our diagram, C is at the location of this open circle, right? And we should expect C to be an element of I, right? And it's not too difficult to show that C is an element of I. To see why, well, since C is an upper bound of S, this means every element of S is less than or equal to C. So in particular, since A is an element of S, A must be less than or equal to C. And further, since B is an upper bound of S and C is the least upper bound of S, this means that C is less than or equal to every upper bound of S. So in particular, C must be less than or equal to B. So these two inequalities tell us that A is less than or equal to C is less than or equal to B, which means C is an element of the closed interval I. And now that we know C is an element of I, we know that C is an element of the domain of F, so we can send C into the function F. And the claim is that f of C is equal to W. If we can prove f of C is equal to W, well then, C cannot be equal to A or B. Because if C was equal to A, well then, f of A would be equal to W, and f of A would be less than W, which is absurd. Similarly, if we had C equal to B, then we would have f of B equal to W, and f of B greater than W. But that's not possible. So, if we can show that this is true, then that will tell us we have C, which is an element of I, but not equal to A or B. Therefore, C would be an element of the open interval A comma B, such that f of C is equal to W. And the proof will be complete. How are we going to prove this? Well, let's assume for a contradiction we instead have that f of C is not equal to W. The whole goal from here is to reach a contradiction. If we reach a contradiction, then that tells us that this assumption is wrong. So we must instead have that f of C is equal to W, and the proof is complete. So, since f of C is not equal to W, well then the distance between f of C and W on the number line is greater than 0. So absolute value f of C minus W is greater than 0. Divide that by 2, it's still greater than 0. Now, since f is continuous on I, we said earlier that means that f is continuous at every point on I. Well then in particular, f must be continuous at C. So we're going to replace k here with C. So we know that f is continuous at C, which means we know that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number absolute value of f of c minus w over 2. So we're going to take epsilon here to be absolute value of f of c minus w over 2. If we do that, well then, what we get from this is that there is a delta greater than 0 such that for all x in I, if the absolute value of x minus c is less than delta, then the absolute value of f of x minus f of c is less than absolute value of f of c minus w over 2. Now from here, if we give ourselves an arbitrary element x in I such that absolute value of x minus c is less than delta, well then, we know that this inequality will be true. But we can re-express this inequality in a different way. If you recall, we have the following property regarding absolute values. Given any two real numbers a and c, to say that the absolute value of a is less than c is equivalent to saying that the negative c is less than a is less than c. Right? So if we apply this rule to what we're doing right here, well, this is equivalent to saying f of x minus f of c lies between the negative of this and the positive of this. So for any element x in I such that absolute value of x minus c is less than delta, we have that this is true. And so we're going to be referring to this fact a few times for the rest of our proof. And so I'm going to call this fact star. And so because we ran out of room, we're going to move back up to the top. Now remember, we are working under the assumption that f of c is not equal to w. And the whole goal is to reach a contradiction. Now since f of c is not equal to w, well, we can consider two cases. Either f of c is greater than w, or f of c is less than w. And what we're going to do is we're going to show in either case, we reach a contradiction. That will tell us our assumption that f of c is not equal to w will lead us to a contradiction no matter what. So, let's start out by considering the case that f of c is greater than w. So how are we going to reach a contradiction in this case? Well, let's think about what's going on in our function around c. So this is where c is, and the output value it yields to the function f is f of c. And f of c is greater than w in this case. So we're going to say w is about right here. Now, c is an upper bound of s, which means every element of s must be to the left of c. Also, since c is the least upper bound of s, there can't be any upper bound of s to the left of c. Well, in this case, we're going to actually show that there is an upper bound to the left of c, and that will contradict the fact that c is the least upper bound of s. To see why we should expect there to be an upper bound to the left of c in this case is because we know that to be an element of s means the output value yield through the function f is less than w. Well, if we're right here, then f of x is greater than w, so you're not an element of s. Similarly, if you're right here, not an element of s. Anywhere in this region, you're not going to be an element of s. But then all of a sudden, once you become less than w, say about right here, all of a sudden, you are an element of S. So remember, every element of S is to the left of C. But also, every element of S must be to the left of this line as well. Therefore, any element in this region we expect to be an upper bound of S. And that contradicts the fact that C is the least upper bound of S. So, that's what we're going to do. We're going to show that there's an upper bound of S to the left of C. In particular, we're going to show that C minus delta is an upper bound of S. And this will contradict the fact that C is the least upper bound of S because C minus delta is smaller than C. Okay, so to show that C minus delta is an upper bound of S, we want to show that every element of S is less than or equal to C minus delta. So let's consider an arbitrary element in S, called X. The goal from here is to show that X is less than or equal to C minus delta. Well, what happens if instead we have that X is greater than C minus delta? Well, from here we want to reach a contradiction. Because if we reach a contradiction, that will tell us that our assumption that X is greater than C minus delta was wrong. And so we must instead have that X is less than or equal to C minus delta. Well, if X is greater than C minus delta, then C minus delta is less than X. We know that since C is an upper bound of S, X must be less than or equal to C, and C is less than C plus delta. Now, this chain of inequalities tell us that C minus delta is less than X, which is less than C plus delta. Notice if we subtract C on all three sides, we get negative delta is less than X minus C is less than delta. But then, by the fact we have here, this is equivalent to saying that the absolute value of X minus C is less than delta. And so, ultimately, this chain of inequalities tells us that absolute value of X minus C is less than delta. Now, we also know, since X is an element of S, X must be an element of I. So X is an element of I, such that absolute value of X minus C is less than delta. So we can apply statement star. Right? Statement star works for every element in I with this property. So in particular, it must work for the X that we introduced into our proof right here. So taking X to be the X we introduced into our proof, we have that this inequality is true. Now, we're actually going to be concerned with the left-hand inequality in this case. So f of x minus f of c is greater than this guy. Now, since f of c is greater than w, the absolute value of f of c minus w is equal to f of c minus w. So really, this guy is just equal to this. And then, if we distribute the minus sign across the numerator, this is really just w minus f of c over 2, which is equal to w over 2 minus f of c over 2. So really, f of x minus f of c is greater than w over 2 minus f of c over 2. Well, if we add f of c to the other side, we get that f of x is greater than w over 2 plus f of c over 2. But then, since f of c is greater than w, we have that f of c over 2 is greater than w over 2, and therefore w over 2 plus f of c over 2 is greater than w over 2 plus w over 2, which is equal to w. And so f of x is greater than w. But since x is an element of S, we know by definition of S, f of x must be less than w. But this contradicts the fact that f of x is greater than w. So our assumption that x is greater than c minus delta led us to a contradiction. So we must instead have that x is less than or equal to c minus delta. And then, since x was an arbitrary element of S, we have shown for all x in S, x is less than or equal to c minus delta. And that tells us c minus delta is an upper bound of S. So, c minus delta is an upper bound of S. But as we stated before, this will contradict the fact that C is the least upper bound of S, because C minus delta is a smaller upper bound than C, which is the least upper bound. So, the case f of C is greater than W leads us to a contradiction. So, now let's consider the case f of C is less than W. Now again, in this case, we want to show we reach a contradiction. Now, to see what contradiction we're going to reach, well, let's consider again the graph of our function around C. We'll say that this is C, and the output value it yields to the function f is f of C. And in this case, f of C is less than W, so W is maybe right here. Now remember, since C is an upper bound of S, we know that every element of S is going to be to the left of C. But in this case, we can actually show that there are elements of S to the right of C. For example, this guy we expect to be an element of S because, well, as you can see, the output value it yields to the function f is less than W. And that's precisely what it means to be an element of S. So we're going to show that there exists an element to the right of C, which is an element of S. And that will contradict the fact that C is an upper bound of S. Put another way, we're going to show that there exists an element M in S, such that M is greater than C. Right? But this contradicts the fact that C is an upper bound of S, because what does it mean for C to be an upper bound of S? It means that every element of S is less than or equal to C. So in particular, we would also have that M is less than or equal to C, and that contradicts the fact that M is greater than C. Okay, now in particular, we're going to take M to be the following value. We're taking M to be the minimum of B and C plus delta over 2. And the claim is that M is going to be an element of S, and M will be greater than C. Let's first show that this choice of M is going to be greater than C. To show that M is greater than C, all we have to do is show that B is greater than C and C plus delta over 2 is greater than C. Because we know that M is equal to one of these two values. So if we can show that both of these values are greater than C, that'll tell us that M is greater than C. Now, first of all, clearly C plus delta over 2 is greater than C. But how do we know B is greater than C? Now, since C is an element of I, we know that A is less than or equal to C is less than or equal to B. So, at least we know C is less than or equal to B. Right? Or I'll write this as B is greater than or equal to C. So we know B is greater than or equal to C, but we want to show that B is strictly greater than C. Well, what happens if B is equal to C? Well, if B is equal to C, then we can replace C here with B, and we have that f of B is less than W. But also, by our hypothesis, W is less than f of B. But this is absurd. We can't have W greater than f of B and W less than f of B. Therefore, assuming B equals C leads us to a contradiction. So that eliminates the possibility that B is equal to C. We must have that B is strictly greater than C. So C plus delta over 2 is greater than C and B is greater than C. And that tells us that M must be greater than C. So we have shown that our choice of M is greater than C. Now all that's left to show is that our choice of M is an element of S. How do we show M is an element of S? Well, we got to show that M satisfies these two requirements. So taking S to be M, we want to show that M is an element of I and f of M is less than W. To show that M is an element of I, we have to show that A is less than or equal to M is less than or equal to B. Okay, now since M is the minimum of these two values, this means that M is less than or equal to both of these guys. So in particular, M is less than or equal to B. So M is less than or equal to B. but also we now know that m is greater than c. And then let's recall, since c is an element of I, we know that a is less than or equal to c is less than or equal to b. So in particular, a is less than or equal to c. Just like that. And so we see that a is less than or equal to m, which is less than or equal to b, which is exactly what we wanted to show. That tells us m is an element of I. And so we have shown that m is an element of I, so all that's left to show is that f of m is less than w. And to show f of m is less than w, we are going to apply statement star. Now, to apply statement star, we need m to be an element of I, and we need the absolute value of m minus c to be less than delta. Well, we know that m is an element of I, that's what we have here. But we don't yet know that the absolute value of m minus c is less than delta. That's precisely what this second element is for, right? We know that m is less than or equal to b, and m is less than or equal to c plus delta over 2. So in particular, m is less than or equal to c plus delta over 2. Now, since delta over 2 is less than delta, certainly c plus delta over 2 is less than c plus delta. Also, we know that m is greater than c, and c is greater than c minus delta. So what does this tell us? Well, we have that c minus delta is less than m, which is less than c plus delta. Right, this looks familiar. If we subtract c on all three sides, we get this, but then we just apply the fact that we have here. And so we have absolute value of m minus c is less than delta. So now we know m is an element of I, and absolute value of m minus c is less than delta. So we can apply statement star to m. By star, this inequality is true where x is replaced with n. And in particular, we care about the right-hand inequality in this case. So f of m minus f of c is less than this guy. And on the right-hand side, since f of c is less than w, we know that f of c minus w is negative. So the absolute value of f of c minus w is equal to w minus f of c. So like this. But then this is equal to w over 2 minus f of c over 2. And then notice we have f of m minus f of c is less than w over 2 minus f of c over 2. Adding f of c to the other side, we get f of m is less than w over 2 plus f of c over 2. And then, since f of c is less than w, we have f of c over 2 is less than w over 2. Therefore, w over 2 plus f of c over 2 is less than w over 2 plus w over 2, which is equal to w. And so f of m is less than w. And so we have showed that m satisfies the other requirement to be an element of S. Therefore, m is an element of S. So we have shown that m is an element of S, and we also showed before that m is greater than c. And so, because we've shown that, well, this leads us to a contradiction, because c is an upper bound of S, right? We have that m is greater than c, but since c is an upper bound of S, this means every element of S is less than or equal to c. So not only is m greater than c, but m must also be less than or equal to c. That gives us a contradiction. So if f of c is less than w, we get a contradiction. So putting this all together now, we have shown if f of c is greater than w, we get a contradiction. If f of c is less than w, we get a contradiction. So no matter what, we reach a contradiction. So our original assumption was that f of c is not equal to w. From there, we considered two cases. Either f of c is greater than w or f of c is less than w. Both cases reach us to a contradiction. So our assumption that f of c is not equal to w will lead us to a contradiction no matter what. So our assumption that f of c is not equal to w was wrong. We must instead have that f of c is equal to w. And from earlier, we stated if we have shown this, then this implies c must be an element of the open interval a comma b. And so we have found an element in the open interval a comma b where if we send that into the function f, the output value is w, right? Just like that. And so this completes the proof. And so yeah, that's pretty much it for this video.